Welcome everyone back to our second PCAST talk. We'll go ahead and get started for today. So before we begin with our speaker, I wanted to do just a few community announcements for everyone. So in case folks have not seen already, we're excited to announce that Volume 2 of our GEO General Observer book is now accepting submissions. And so you can find more about this on our webpage. Submissions will be due at the end of May. And we encourage you, if you're interested in doing a submission, to attend our community webinar, which is going to be tomorrow. And we'll have 2 sessions to accommodate folks in Japan and Europe and the US. And so you can register for this online. I'll put both of these links in the chat once I'm done talking. We will also be, just like these talks, recording this webinar, both sessions of it, and making it available online so that folks can reference it after the fact and see if their questions are answered. So we're also excited to announce that our working groups are getting ready to restart at the end of this month. So we're hoping to get these moving this week. We are going to be doing the initial coordination of these working groups through Slack. So if you did sign up, please watch your email this week. There will be an invitation to join the Slack workspace and to self-select into the working groups that you're interested in. We have sort of an initial notional list of these working group areas and are currently populating the leads. So you can see what these are going to look like, and we certainly encourage folks, if they have multiple interests, to feel free to join multiple of these working groups. So coming up, we have more talks. So next month, the same date, March 24th, we're going to have Qi Zhang talking about protoplanetary disks. And the following month, we'll have Joachim Basselmans talking about detectors, with more talks to follow throughout the summer and next fall. But of course, today, we're all here to hear from Erini Lambrides, and she's going to be telling us about high redshift obscured AGN with PRIMA.
So hello, everyone. My name is Dr. Erini Lambrides. I'm an NPP fellow at NASA Goddard. And when I was thinking about, developing this talk and refreshing myself on some of the initial geoscience book, volume 1, I guess, and some of the other conversations, something that I really wanted to give context to in this talk and end up, as the talk was getting made, being primarily focused on is how PRIMA is really necessary and really important in breaking some of the degeneracies in our understanding of competing models that are being uncovered with JWST, especially in the first half of the universe. So the initial intention of this talk was a much broader scope of obscuration, which is what I normally focus in. But I think that aspect of the obscured AGN type community has been moving and progressing so fast. I really wanted to help give a little anchoring to people who are kind of observing all the chaos that's happening with AGN and JWST outside the field, and give some context. So with that being said, the main trope that really makes AGN quite exciting, or growing supermassive black holes quite exciting for people like myself and people who just care about the galaxies, is trying to understand when you're looking at images of deep fields, this is from Cosmos, is how do we go from when we're looking at these images of moderate to deep fields of so this is from Cosmos Web, taken with multi-band JWST near-cam imaging. Only a small percentage of all these dots you see here, which are primarily galaxies, have a supermassive black hole that is actively accreting and growing. And how are we connecting the growth of that supermassive black hole, their galaxy, and within a much larger scale environment? And so this kind of just summarizes the past efforts of the past, since 1962, when the first accreting object that we now know to be an accreting supermassive black hole was discovered, is understanding, what are the directions of these arrows, what matters most. Are galaxies really drivers for what the growing black hole in the center looks like, or vice versa. And when does it matter, and what epochs are these relevant, and what scales do we expect to see the biggest change and the biggest impact? And so as an AGN, astronomer, quite blessed, because the phenomena of a growing supermassive black hole has signatures across the entirety of the electromagnetic spectrum. But primarily in terms of the amount of telescopes on the ground and in the sky that have existed, we really have had a wealth of coverage and data coming from the UV optical. And we have obviously have made concerted efforts in the X-rays and mid-infrared and beyond. But by and large, some of the largest surveys of AGN and a lot of the new telescopes that are confirmed, especially new flagship telescopes that are confirmed, tend to be between UV optical to near infrared. And although JWST has this mid-infrared observed instruments, most of the questions that we've been asking about AGN are centered at epochs in the universe where the rest frame is no longer in the mid-infrared. And we already know from many decades of search that AGN are also going to come in different flavors. And for most of cosmic time, a lot of studies are indicating that AGN, how these flavors present, is predominantly by their orientation or their sightline. And so you have unobscured or obscured, and I'm going to go into a little bit more in a second on what I mean about that. But basically, in a sightline only view of how AGN present, you have your growing accretion, you have your black hole surrounded by an accretion disk, surrounded by some sort of clumpy molecular torus of material. And if your telescope sightline is going through the edge or some angle that intersects with that torus, then you're going to get an attenuation of light that is primarily going to be impacting the wavelengths shown here. And so the redshift 0 universe was really revolutionized by access to the rest frame mid-infrared. And especially, when you have much wider all-sky surveys like WISE and Spitzer, which also had the much more deeper surveys that were focused on, legacy fields in addition to wider surveys of the sky. These two combined together really opened this big avenue of study on how do we constrain the difference between sightline or evolutionary effects of how AGN present, and how might this impact the properties of their host galaxies. And one of the really big lessons learned is just how prolific the infrared was at identifying large numbers of AGN across large epochs of cosmic time. And even, to this day, this, notion that, the infrared really is the best way to try to select your AGN predominates. But an important thing to note is that most AGN are not quasars. So most of these growing supermassive black holes are going to be black holes that are in galaxies that have potentially commensurate amount of bolometric emission from their star forming processes. And so this really impacts color selection methods. So even the color selection methods that were being used with WISE or with Spitzer, you're going to be predominantly selecting the most mid-IR AGN dominated only sources. So if you're having a lot of mid-infrared contribution due to star formation processes, these color selections also tend to have a lot of bias and completeness issues on that front. And so the other thing to note, though, that Spitzer uniquely really helped us with is the rest frame mid-infrared spectroscopic coverage. And so what we learned is that, we know that there's a wealth of spectroscopic information in the mid-infrared that really helps look at in situ probes of star formation and AGN simultaneously. And despite the fact that we don't have, at the time, the sensitivity to really take that out to higher redshifts, what we did learn was that there were certain regions that of the spectrum that were really, really good at helping to disentangle this AGN versus star formation contribution. And one of my favorite is looking at around the rest frame 6 microns, where you will have hot dust being dominated by the AGN. And in cases of only the most evolved stellar populations can you get really commensurate amounts of hot dust coming from stars. So it's really good to, and even then, for most AGN, for most luminosities, the hot dust coming from close to the growing black hole is really going to be dominating that region. So we could use that knowledge to go back to using some of these photometric bands and doing multi-wavelength selections of AGN. In this case, this is looking at the rest frame 6 microns compared to the X-ray luminosity. And the X-ray alone was listing these sources with especially the blue points that you see on here, sources that didn't seem to have significant amounts of obscuration. But when you combine the X-ray and mid-infrared, you see that the X-rays were really undercutting the amount of obscuration that was attenuating not only the X-ray emission, but really in some cases in the catalog, some of these sources are listed as galaxies and not AGN. And only when you combine rest frame mid-infrared to this are you able to understand its true nature. And so in addition to having these dust contributions, we also have ionization lines that have been really helpful and really prolific in telling us the relative contribution of star formation and AGN activity. And they're much less impacted. And they're than some of the obscuration issues. And as we go redder into the rest wavelengths, we're really seeing how these are very, very useful tools and probes of identifying AGN. So we've kind of amassed this knowledge of really kind of eking out the most that we could from Spitzer and WISE, and I'm sure there's still questions that can be answered in the archives or would really be informed by data in the archives. But especially at the lower redshift universe, we were primarily focusing on studies that exploited the fact that in obscured sources, in the rest optical UV, you're going to be having emission that's dominated by stars. So obscured AGN are really great for asking questions about host galaxy and host galaxy potential impact due to the AGN. But for the most part, not very, very strong evolution was found between some of these properties like obscuration and the type of AGN that you were looking at. But as the quest continued to understand the AGN phenomena at higher and higher redshifts, we lost access to the rest frame mid-infrared. And so we were using our anchoring of, what the mid-infrared could and couldn't tell us at the lower redshifts to make predictions on what we expect we should find at higher redshifts without actually having that rest frame mid-infrared coverage to confirm that. And so pre-JWST, at especially the highest ends of cosmic time, so as we're going to, above redshifts 5, we would use Sloan, primarily, and then do a lot of follow-up studies, or use WISE selected sources and do a lot of ground-based follow-up studies to try to find the highest redshift AGN. And a lot of these AGN were very bolometrically luminous. They were quasars. And they were selected to look like the AGN at lower redshifts. That's how the selection methods were devised. And so we found a handful, growing number of very high redshift quasars. And we're kind of building our picture of how important AGN were for galaxies in the early universe, and how that might connect down to more intermediate redshifts. And so at the highest redshifts, there was this idea that, AGN might really not be that important for most of the processes going on in massive galaxies. And that's really kind of exemplified here in this plot, where you can really see many orders of magnitude difference in the number density of these optically luminous high redshift AGN compared to the total number of massive galaxies at high redshift. And so for the broader galaxy evolution community, at high redshift in particular, AGN were interesting for the AGN people, but maybe not so important to contextualizing or understanding their sources. And so these are examples of some of the early science fields, especially with spectroscopic coverage or slitless spectroscopy, that were performed with JWST. And a lot of them were centered on these legacy deep fields, so Fresco and Jades and Eiger, it's Goods North and Goods South. And people were very excited to see what JWST was going to see with these sources, especially at the faintest end, as we're now able to have sensitivities in this rest frame optical regime at high redshifts that were beyond what we've been able to do before, and in wavelength coverage that we weren't able to do before. And one of the biggest surprises that came out of these surveys is that there was a lot of sources that seemingly looked like AGN. They were very compact. They had reddened SEDs, and they really seemed everywhere. And so these were, three independent collaborations that kind of independently at the same time were coming to this notion. And all the other people with cycle 1 or cycle 2 data, as these papers were coming out, went and looked in their data to see if they could find sources that had some of the characteristics that I'll explain in a sec. And even in study surveys like the Uncover program, which had the opportunity to go photometrically select sources, then go back and get spectroscopic follow-up, was confirming that these really compact and really red and really numerous sources had at least one broad line. So they had at least one line, either most cases it's H alpha, that had a component that was broadened above 1,000, 1,500 kilometers per second, that seemed to be tracing the broadline region gas around a growing supermassive black hole. And, all these other photometric data that existed, in addition to those surveys, but also the collaboration that I'm the AGN lead of, which is Cosmos Web, went back in and looked at our photometry using colors that were color selection that was developed off of these, spectroscopic earlier studies. And we're trying to how many of these sources exist in our data. And it was absolutely surprising to see the level of overabundance at especially the high redshift end that we're seeing of these AGN candidates. So as you can see, it is orders of magnitude above what was predicted prior to JWST. If you just extrapolate rest, UV, optical, luminous AGN, luminosity functions. And we are now getting potentially this idea, oh, are AGN a significant component of the flux that you're going to see in a pretty sizable number of regular massive galaxies at high redshift, things that we're calling not AGN? Has there actually been some contamination? If you ask galaxies people, they'll call it contamination. But for an AGN person, it's very exciting in the early universe. And so this really threw the field in a tailspin, and why you're seeing so many papers come out so fast. And it's very hard to keep up if you're not in the field, because even in trying to explain kind of the story, I know I kind of jarringly jumped from talking about the mid-infrared and all of a sudden talking to JWST. That was kind of on purpose. It is moving so fast that at times it's a little unclear if we're even talking about apples to apples. And the main driver of this excitement is the fact that there's just so many of them, and that it really, if you look at, black hole accretion rate densities, as we do on the plot here, really increase at higher redshifts of the supposed number of black hole accretion rate density. And we're having a really difficult time connecting the higher redshift universe to the more intermediate redshifts, especially at around redshift 1, if this is true. And so another very peculiar aspect of these sources is that they do look very different from the usual suspects, and they look very different from the type of AGN that we would select at pre-JWST times. And so they're ultra compact. There's very little obvious host signatures. In many cases, if you assume energy balance, it underestimates the MIRI detections. And so at these redshifts, I would just want you to take a look at the x-axis on this plot here. Even at the lower end of the redshift distribution for these sources, which is at around redshift 3, we are not touching at canonical rest frame mid-infrared. We're at best below 5 microns, but most of these studies have coverage that's up to 2 microns. And so we're really unable to get into the rest frame mid-infrared on this, which is a problem because we're seeing a flattening happening in the rest frame near infrared that is just not easily explained at all with our understanding of these sources. The other weird aspect is that there's a growing diversity of UV properties, and this could be potentially due to different color selections being applied. So on these two plots here, I'm just showing an example of what a JWST spectrum would look like for these sources in PRISM. So highly sensitive, the widest bandpass, but the lowest resolution. And if you look, below 1 to 2 microns in the observed wavelengths, in the source on the left, there's very little UV emission, and the source on the right, you're seeing Lyman alpha and C4. And this has really complicated our interpretations of trying to explain this peculiar SED that we're finding, which I kind of show here. So this is from the Uncover survey, Jenny Green's 2024 paper, looking at an example of one of these sources where you're seeing the black is the spectrum. Again, once again, this is in PRISM, I believe. And there's this anomalous UV emission for their samples of sources. So this bluer component coupled with a redder rising, seemingly attenuated AGN component. And it's very hard to rectify the shape of this spectrum with any of our canonical obscured AGN models that we have. The SCD fitters fail to do this. Just logic fails to try to explain what these are looking at. There's a lot of variance between the spectra, but the most confusing aspect is trying to explain this V shape that is predominant in a lot of these sources. And so there's a lot of different interpretations on to what we might be seeing here. In the green paper, it was suggested maybe these are sources that are so obscured. The UV slight excess that we're seeing is scattered light. But then that opens questions of why are our MIRI estimates wrong? Why are we overestimating the amount of hot dust that we would expect in this if you were to just, reprocess the AGN emission that we're seeing a little bluer. Some people have said, what if they're just ultra compact star forming galaxies? What if they're not AGN at all? And there's another way to explain these broadened lines. If that's the case, they really eat up a large portion of the amount of massive star forming galaxies allowed in the early universe. And it's what to me would seem pretty peculiar that we would just find the maximum allowed amount of so many sources that are near the maximum allowed star formation surface density. So that's a big issue if you want these all to just be purely star formation driven. And then we still need a way to explain how do you get the broadening of those lines. And so at lower redshifts, when we see broadening in H alpha or H beta due to just star formation processes, you're looking at Euler type galaxies that are merging. There's a lot of outflows that can cause this broadening. And for these galaxies, their O3 and other narrow ionization lines stayed narrow. And it's just the Balmer-Siri lines that one would find any sort of symmetric broadening in. And so it's really hard to rectify the spectroscopic broadening that's being observed with just star formation. And then, one of the ideas that I tossed around was maybe we're wrong about how these sources are accreting. Maybe our bolometric luminosities of these sources are wrong because if they're accreting at much higher rates, there will be a different intrinsic shape to the SED. And that would give you more allowance into not overestimating the amount of reprocessed emission you would expect them in the mid-infrared, because in general, with the accretion model I used in this paper, which I won't go into detail on, it's a much lower effective bolometric luminosity. But I was basically claiming that some of these sources could be evidence of super Eddington accretion. And if a lot of them are being driven by super Eddington accretion, that is another very bold claim. And it would be nice to have some other pieces of evidence to confirm that. And so this summarizes, this is a stack of all the Cosmos Web serendipitously discovered AGN that show the state of where we are multi-wavelength wise with these sources. And that is a lack of multi-wavelength detection in X-rays and radio and in dust. So the other puzzling piece of these sources is that it's been very hard to get an ALMA detection on them. And so some of the explanations as to why the rest frame near infrared isn't rising as steep as you would expect, and why the sub-millimeter observations with ALMA are finding it very hard to detect either both dust continuum or cold gas signatures is, what if the dust distributions look different? What if we're dealing with dust that's not as hot but not as cold? And so there's a large warm component. And so there can be ways that you can make these non-detections work with the bolometric luminosities people are inferring from these sources from the rest optical, but it requires pretty peculiar dust distributions that we really haven't seen before. And so, or dust temperature distributions that we haven't really seen before, but we don't really have the coverage in the rest frame mid-infrared to say whether those hold water or not. So how do we figure out if these things are actually AGN, and how do we contextualize them to the broader population? So in and amongst these sources that exist and were very confusing and surprising are all the other AGN that we know exist there that do look like what we expect them to do. And even prior to JWST in the high redshift universe, we knew we were only looking at the unobscured sources. So we knew we were undercounting the amount of AGN that we would expect to see at those times, and that there should be populations that were obscured, even if it's just a simple sightline argument. But one of the things that was really coalescing for a few years, maybe 5 years prior to JWST's launch, is that there's building evidence that there is an evolutionary connection with obscuration. And in fact, once you get beyond redshift 3, you really start to see that in the number densities of obscured versus unobscured samples, where the amount of AGN obscuration goes beyond just what you would get from a torus sightline argument. And maybe that's not so surprising, because as redshift increases, so does the covering fraction of gas and dust. So the AGN live inside of galaxies that are obviously also evolving. And what you end up getting is the galaxy itself being able to attenuate the central engine itself. And so you can, and we've seen this with comparing X-ray Compton thick candidates, so very heavily obscured AGN that were identified in the X-ray, and following them up with ALMA, and finding you could explain all the obscuration you see in the X-ray off of the ALMA continuum measurements of obscuration and the dust mass from ALMA. And so this was building this idea that we are potentially at an epoch of time, once we go above especially redshift 5, that if your AGN is unobscured, you are not representative of the total AGN population, that you cannot just simply use an unobscured AGN to answer these big questions about what role do AGN play or don't play in the beginning of galaxy formation. And so to connect this back down to the LRDs, or these serendipitously discovered JWST AGN, their primary piece of evidence that their AGN in the first place is coming from signatures associated with unattenuated, it can't be that obscured in order to detect the broadline in the rest optical. Another way they're identified, in addition to spectroscopically with the broadline, is how compact they are. And the compactness, making the argument that it's a point source. And again, with JWST at these epochs, we're looking at rest frame optical. And so there can be some obscuration in these sources, but really heavily obscured, as is indicated by the definitions on the left here, would not have these, as we understand it, these spectroscopic nor morphological signatures of being an AGN. The accretion disk would simply just be too attenuated. And so when you put that all together, and you account for the obscuration, and the green line, the darker green line, is what that looks like before JWST. If you do this with the rest optically luminous AGN found with JWST and try to apply that same correction, you're all of a sudden making a claim that there is an AGN in every early massive galaxy, which is a very, very bold claim. And one of the open questions is, well, if that's true, how does that evolve down to the redshift 0 distribution that we see today? It is very not lost on me that this has very big implications on how efficiently AGN are triggered in the early universe, and what impact this might have on the nascent galaxies that they live in. And so we really need to figure out, how do we find this heavily obscured population? And we don't even need to necessarily even go to the most highest epochs. Just even looking at intermediate redshifts, in between cosmic noon and redshift 7 would, or redshift 6 would be very, very helpful to try to understand how do we connect this big picture evolution of what some of the claims that are being said at high redshift down to lower redshifts. I don't know what these animations are that are in there. I apologize. So at these epochs, JWST nor ALMA can really help us with this. So in addition to the fact that those LRDs just might be weird, even the regular obscured AGN population that you predict, we really need rest frame mid-infrared, and neither ALMA or JWST gives that to us above, redshifts 3 to 4. But PRIMA can really save the day with that. And so with just looking at these mid-infrared powerful AGN, so basically doing what we did with Spitzer and WISE at low redshift, but just at higher redshifts, so finding these mid-IR dominated, AGN dominated sources would really be key and critical for that. And for a more complete selection, so for not just sources that have mid-IR emission that overwhelms their star forming, and that allow those, red color selections to be reliable, being able to actually look at spectroscopic signatures in the rest frame mid-infrared would also be transformative. And so other geoscience books have done this already, so I'm not, in terms of talking about the general obscured population. I am going to tell you what PRIMA could do with LRDs, because I know this has been a big question of, will PRIMA be able to detect, or how helpful could PRIMA be in trying to understand the mysterious JWST AGN that are really dominating the number densities of AGN at high redshift. And so this is a case study of a redshift 3.12. So this is like one of the lower redshift LRDs that was found in the Uncover survey in a study led by Binji Wang last year. And this spectrum that you're looking at here of this source is extending all the way into 20 microns. So the spectrum itself is stopping at around 6-ish microns, and then there's MIRI coverage in imaging up to about 20 microns, and these are observed. So when you do the rest frame correction, these are all below 5 microns and rest. And so when you look at this source, this is highlighting this flattening people observe with the MIRI detections, where it's not rising at the same slope that we have measured for other obscured AGN or hot dust emitting AGN in the past. And in that paper, there was a lot of effort to try to get any sort of clumpy torus model reproduce the peculiar shape of the rest frame near infrared SED, coupled with the upper limits that were given by Spitzer and Herschel observations in redder wavelengths. And it was quite difficult, but when you change the different temperature distributions of, hot relative to warm, relative to cold, there are some models that are able to reproduce and some that don't. And really the story got left as well until we're able to get more constraining power in the infrared. It is going to be very difficult to try to say anything about how we could get dust distribution, temperature distributions to solve this mystery alone. But with PRIMA using low res, the result really could potentially be transformative. And so I know 20 hours with a source, or it was like 20 to 22 hours when I did the estimate for this with a source may seem prohibitive, but I will try to justify to you why it is very much worth it. And so when we're talking about these different temperature contributions that we're getting, both from the dust and gas in these regimes, a lot of the rest frame near infrared catered view of these sources is saying that there's a deficit of hot dust. They're only able to probe out in most cases to 3 microns, but they're using that point to say that, so that would be around here, and they're using that point to say that there is a deficit of hot dust. They're unpredicting the amount that they're getting here, but it leaves the question open of, one, if we were to able trace a little bit more, go a little bit redder, would we see that it's not that there isn't any hot dust, there may be less hot dust than we thought. It's a continuum. Maybe the distribution looks different, and also the relative amount of warm dust, which is currently unconstrained in these sources. And so with Spitzer, use IRS, the equivalent width feature, the equivalent width of the pH 6.2 feature, even in the low resolution mode, was very helpful in finding any evidence of an AGN, even in lower luminosity sources. So let's say the bolometric luminosities of these sources are being overestimated. So we're overestimating the amount of reprocessed emission that we would expect from the near infrared to mid infrared. So they're great at selecting AGN even in low luminosity situations. And when you have significant amounts or comparable amounts of star formation within the galaxy. And so when you are, in addition to all the other lines that you would get if you were to do a FIRIS observation of this specific LRD here, in general, you would, without a doubt, in all different cases probed so far on what the nature of the source could be, within, under 25 hours or around 20 hours, would be able to constrain which of those models hold more water than others. So in particular, if this source was AGN dominated, and the AGN is really driving the emission in the rest optical, but the bolometric luminosity was being underestimated, even with a reduced bolometric correction, you would still be able to detect the continuum within that region, to get an equivalent width measurement to confirm that. If it's star formation, the pH 6.2 microns would very easily be detectable. And so we really are at a place right now, especially with the LRDs, that it's data we don't have that will help rule in or rule out what some of the competing models of these sources are. And with investment from PRIMA, it can really allow us to say what implicate, because no matter what these sources are, they have an impact. There's just so many of them. So whether it's star formation, whether it's AGN, and PRIMA would uniquely be able to really give an important piece of the puzzle in understanding which sector of astrophysics this impact will be felt in. And let me just check on time here. Yep, almost done. And so the PRIMager also would be just doing a survey with the PRIMager in, let's say, the inner region of Cosmos Web. So this is about 0.3 square degrees. And the reason why I said 0.3 square was because it overlaps with the slitless spectroscopy that is being taken with Cosmos 3D program. Amongst all the other science that just exists in there, for the brightest LRDs in Cosmos Web, we'd be able to probe the peak of the warm dust emission. And so these are just, this is an unexplored discovery space territory. JWST and ALMA have not been super elucidating, especially because some of the explanations on the mysteries of these sources are centered in questions about their dust temperature, dust distributions, and we're completely missing a phase of the ISM that is only accessible at these epochs with the observed frame far infrared. So I will leave it at that. And yeah.
Wonderful. So let's thank Erini and take some questions. And you're welcome to, all right, Alex has her hand raised.
I'm just going to stop sharing my screen so I can see, and I will reshare.
Hi, Erini. Thank you. That was a great talk. I wanted to ask you about, at the end of the bit on the JWST AGN, you showed the plot of the, the number counts or luminosity function or something, showing that if every massive galaxy contains an AGN at those early times.
Yeah.
And I think you kind of alluded to, you're wondering how that fits in with later times. And so I guess my question is related to that. Has somebody worked out how much black hole mass is built up during, assuming every galaxy is growing its black hole during those early phases? I know it's a short amount of time, but we know it has to grow a lot later because we have the black hole accretion rate density. So does that violate any low redshift local measurements?
Yeah, so that's a great question. So if so one of the things that this is kind of re-explored is how there's two things we know to be true. We can't have more black holes than we observe at redshift 0. And in terms of the black hole accretion density measurements, the Sultan argument basically is telling you the amount of bolometric luminosity you can have at early times in order to not violate what we observe at lower redshifts. And so, I'm sorry, I don't have my notifications muted, so I hope no one says anything crazy. But so it all comes down to they can be growing and accreting at faster rates, but how much does that bolometric luminosity, how much that corresponds to its bolometric luminosity will impact if it violates it or not. So if you have an accretion model that's radiatively inefficient, then you have a lot more wiggle room for how much you're allowed to just boost out there. And so, yeah, there's definitely limits that are placed, but there is wiggle room in the number of AGN that you can have in the early universe that doesn't completely violate. And then there's the question of, how well were we parametrizing these sources at redshift 2 in the first place, and how much wiggle room is there in our black hole accretion density measurements at cosmic noon, where the peak of AGN activity is. And so people are a little less concerned about that, but I have heard arguments that if there's underestimations that are happening there, then that might also alleviate some of the tension.
Okay, thanks.
I don't know how much I believe them. I'm just giving.
Yeah. Okay.
I do think that there is wiggle room at high redshift though for.
Okay.
But we need to see those sources evolve down, and specifically with the LRDs, which. So even if you take away this, where's the canonically obscured sources? If you just look at the LRDs, it is unknown what those turn into. And we don't have enough wavelength coverage of them to properly contextualize them to broader AGN samples.
Thanks.
Great. More questions, and you can raise your hand or enter them in the chat. Margaret.
Thank you. That was a really inspiring talk. I am curious. This is not my field, but I'm curious because when people talk about like seeing really luminous things, they talk about needing like super wide field surveys to capture those rare few and stuff. But I get the impression from your talk that we don't need to do that. And I was just wondering if I understand that correctly, or does it warrant to have like a big field and you'd find something?
Yeah, no, that's a great. Yeah, so yeah, in general, the rule of thumb was the more luminous, the more rare, so more area needed to build up significant samples. The number density, though, of especially these serendipitously discovered JWST AGN, they were first discovered in pencil beam size areas. So, you know, really small fields, especially the ones, most of them were found in the initial samples were coming out of Goods North. The canonical little red dot paper that named them as little red dots came out of the combination of Goods North and Goods South, with the majority of them being in Goods North. And so, another handful from a couple of other, again, smaller fields. And so we're really seeing that because of this overabundance of them, that even in smaller areas of the skies being probed, you are still building up sizable samples.
Thank you.
Lee, go ahead.
Erini, I had a question. What fraction of the LRDs show the broad line?
So for the studies that have had the spectroscopic follow-up, it's 70%.
70% of what number, and how were those selected for the spectroscopic follow-up?
So they were selected using a red color criterion, using the two redder near cam filters, and a little bit of blue, like a slight blue excess. So this was in the Labe 23 paper that was just looking at the photometry, where the initial color selection came up on the uncover sources. And then those sources were then followed up on with the near spec prism. That's where you get. So the main contaminant that could happen in these sources is brown dwarfs. And I think a couple of brown dwarfs were found in that selection. But that, in terms of when you take away the brown dwarfs, yeah, it's about 70% that have a broad line.
But it's 70%. I know. Okay, so how many LRDs are there, and how many went into that sub-selection? I'm trying to understand the actual number of sources with broad lines compared to the total population.
Yeah, so So you will get a better answer on this in literally a year, because a lot of the cycle 3 JWST studies are getting the spectroscopic follow-up for the larger numbers of samples. But from Jenny's 2024, I think it was, I actually don't remember off the top of my head, but it's under, it was a, I don't know, maybe, I don't remember actually. I can literally look it up and I will put it in the chat. But it's not a prolific number. It's
right,
like
that's what I thought. It's still, it's right. It's incredibly interesting and exciting, but I think it's still small. But so maybe we'll know a lot more.
Yeah,
in a few months.
With the slitless spectroscopy. So the samples of spectra between all the papers is usually, 20 sources in different fields. Cosmos 3D will be slitless spectroscopy over 0.3 square degrees. And so there's about 400 LRDs that are photometrically selected there. And that will be a much more robust, that'll be a much more robust number that comes out of that.
All right. I think we're still at numbers of sources with broad lines of about 10 or 15, maybe something like that.
I would say per like, so in Fresker and Eiger, that was like 15 sources. The Uncover survey, another 15 sources. In Sears, I think they have 8 sources. So I guess if you combine them all together, it's above 100. But in each individual survey, that doesn't go above 20.
Okay. No, thanks a lot. That's we'll keep paying attention. If a lot more are going to come, if you think a lot more are going to come out, we should really be watching for this.
My personal take on this is, I think the photometric selection is not allowing us to compare too much apples to apples. And that the spectra that we're getting from JWST in certain wavelengths are really diverging, especially in the rest UV. The properties do seem really different. And so I think it's hard to really say anything about them super conclusively without redder coverage, in my opinion.
Cool. So that's a great note to end on. Thank you so much, everyone, for joining us, and we hope to see you again next month. Thank you, Erini.